So, my name is Baptiste Esteban. I am a PhD student at the EPITA Research Laboratory, and I'm going to talk about the cost of dynamism in static languages for image processing. First of all, we're developing an image processing library, and we want it to respect three criteria. The first one is genericity, meaning for one algorithm to take into argument and process several kinds of images, such as images defined on 2D regular grids or vertex-weighted graph or edge-weighted graph. And if I apply on this algorithm a segmentation, and this says data structure a segmentation algorithm, it should work if the data structure respects some constraint. The second thing we want to have in our image processing library is performance, because it's important when doing a real-time application of processing large image. And the last thing is interactivity, meaning we want to interact at runtime with our program without having to recompile everything with static languages. To implement this kind of library, and for my study here, we choose to use two languages, C++, which is the language which implements our image processing library, and because it's a performance-oriented programming language and it supports genericity through templates, but also the Rust programming language, because it's a modern language which is memory safe, and it has the same properties as the C++, meaning that it's a performance-oriented programming language, and it supports genericity through generics and traits. So let me dive a little into generic programming. Here, we have a function called sum. This function takes a vector of integer element and return the sum of all the elements. The main issue with this kind of function is if I want to use a vector of floating points element, for example, I will have to rewrite this function. It's a lack of reusability, and it increases the amount of code to be maintained. So on the other hand, I have a generic sum function. This sum function takes a vector of of element of type T, so T can be any type, while it respects a given interface. In the case of the sum function, T should be default constructible in C++ and should have additive properties. And it increases reusability abilities, and it's just one function to maintain. So now I have defined genericity. I want to define an interface for image to be applied in generic algorithm. So an image is simply a mapping from a domain to a value space. So the domain can be any kind of geometric structure, such as a 2D regular grid or edge-weighted graph, and so on. And it's a mapping from a domain to a value space. So a value space can be any kind of element, and in image processing, it's used to be either an integer or floating point number for grayscale images, or a triple of element for color images. And from this mathematical definition, we can define an interface. So we will have, so any element P of my domain omega will have a type of point type. Any element V of my value space will have the type of value type, and then I can iterate on this as two sets. So if I want to iterate on my domain, I call the function domain, which will return me a range of point type elements, and same thing for values, which will return me a range of value type elements. Then if I want to access a precise value of my image, I will just call the calling operator, which will accept a point type and return a value type. So applying these two image processing, for example, here I have an element-wise operation, which will compute an operation between two images, between all the elements of two images. Without genericity, I will have to write several functions for each kind of image I will have, such as a 2D image or a graph. And we see that here this is two function, image 2D max and graph max, have some similar patterns. So they traverse the image, and the two apply an operation taking into argument one element of the image A and B and storing it into the image out. So with genericity, I can only write this once with a simple for loop which will iterate all the domain, whatever the element of the point P in the domain, and I will be able to apply my operation, which is not restricted to maximum as above, because I can give several kind of operation. And the only restriction, which is not here by an issue of space in my slides, they have to have the same domain. Over, we have some issues with C++ and Rust. Both languages are static. That means the usage of template or generics in Rust is a compile time process. So I have to know the information of type in compile time. And the two languages use a monomorphization process, which will generate specific code for any combination of template. So at each combination, I will have a new machine code generated. So with this, I don't respect the genericity criterion I explained at the beginning of the talk. So usually some people, when doing interactive image processing application using library with templates, specialize for all possible combination of type. The first trouble is it would lead to a combinatorial explosion, to specialize to all domain type, to all value type, to all operation type, and so on. And in the other side, it will generate code for all possibilities, leading to code bloat. So we need for a generic image at runtime. So for the rest of the talk, I will just focus on the value type of my images. So my images will be defined on a 2D regular grid, and we decide to define model based on type erasure. So type erasure is a pattern design which will erase the type inside an object. So for example, it's used in several STL containers such as stdne and std function. So in stdne, it will just store in a space in memory without type an object. So here we have two kind of buffer, a buffer with statically typed value and a buffer with dynamically typed value. They have the same interface, but their implementation detail is different. Here I store a buffer of that of type T, and here I store a buffer of a type erased element, but I need to keep the element size information to be able to traverse my images. So the advantage here is I won't generate more than one images, but I will have to make the conversion at usage, because here I'm returning an address which is type erased. So right now, I have defined the type erasure and values, but my images can be implemented in several different ways. So there is a buffer I presented you, which is a contiguous array, but I can also have an image with where at every point I have the same value. So we will prefer to use a constant than a buffer, because it will be more memory efficient. And we can have on-the-fly computation of images value, so a view as Michael presented in the last talk. So to do this, we also use type erasure. So we will store our image implementation in a type erased space in memory, and we will access it, the element of this image, through a certain operation. So here I use std function, which store a callable object type erased in memory, and the calling operator of std function will just give access and will be called in the callable operator of my two data structure. So they have the same interface as the previous model I have shown you. And we have defined them for statically type value and dynamically type value. The first trouble with this is it adds one level of indirection. That means I have to call my function in std function. So after having defined the form model of images, we have to apply them on algorithms of image processing algorithm, and we want to write generic algorithms only once. That's still our objectives. So we are based on the qsort C library function, which take a table with some information about the table, and one operation, which is here a comparison, and which will sort this type-erased table by taking into argument for the comparison the two elements. It will then convert, compare, and return 1 or 0 in or -1 related to the order of the two elements. And we do almost the same thing. Here we have a function apply. This function take as argument an image and an operation, and it iterates all the image domain and apply an operation in place on an image value. This function can be ever used as statically, so using the statically type value. So here we will have the buffer 2D and the operation, which will be used here in apply. We won't need to have a type conversion here in the operation because it's defined statically. And here we will have an apply dynamic, which will take a dynamically typed image and an operation in the same way as qsort, and we will call apply on it, and first it will convert the value, then apply and store in the type-erased image. But this second apply dynamic will add again another level of indirection. So now we have defined our image model and defined how to use them into image processing algorithm. We will evaluate them. So we compare the performances through three image processing algorithms: the element-wise maximum, the dilation, and the max tree, because they have three algorithmic scheme different. And in terms of performance, I see that every time I add one level of indirection, so ever my value are type erased, or ever my implementation is type erased, I have a certain cost in terms of performance compared to the statically typed with direct access to the buffer. So indirection at runtime prevents some compiler optimization, such as auto-vectorization and inlining. But there is something interesting here, is depending on the algorithmic scheme used. So for random, for example, as the cost will be lower than for the other algorithmic scheme. Last thing I want to show is when I told you that generic programming in Rust and C++ was generating machine code. I thought it was a trouble, and we evaluate the usage of our dynamics or type-erased value, then with operation defined, with a fully templated code, and we see that the fully templated code increases the size of the produced binary very faster than for the usage of operation-based type-erased implementation. So to conclude this presentation, I presented 4 image models, and I adapt generic algorithm to handle all disease models, and we compare the performance related to a different algorithmic scheme. So we conclude that the importance of the choice of the genericity model between the 4 image model depends on the algorithmic scheme. And in the future, we plan not to be limited to the value space, but also to the domain, so to extend our model to other spatial structure. We will modify the existing algorithm in Python to handle the concept I have exposed you. So Pylen is a library I work in with Mikkel too. And we will develop an hybrid solution to reduce the gap, the cost of Dynamism, either by JIT compilation on operation on external module. And at the end, we want to add some interactivity to our library through Python bridge. Thank you for your thank you for your attention. Do you have any questions?
Let's thank this feedback. Do we have questions?
Yeah.
Maybe you come otherwise.
Oh, yes.
Sorry.
Okay. So thank you. Is it okay?
No. I don't think.
You don't think?
You can move.
No. Well, so
No, talk.
maybe. Oh, okay. I will have to speak. Okay. So thank you for very interesting talk. And so what you want to do is essentially also do some kind of runtime coordination, runtime code specialization. So not just static compile time.
No. Yeah, that's it.
Yes, but there also in a very different context, there are programming language which provides runtime coordination facilities such as MetaOCam and so on. So which is quite different language, but then also of course you want to obtain a very powerful, high performance code written in C++ or something like that. But you can still use that kind of MetaOCam like high-level language to generate low-level language by heterogeneous metaprogramming. Have you ever heard of that?
I understand what.
Can you comment on this kind of
Okay, if you want, I can comment on. If you want, I can comment on what you're asking. The fact is, Pylen is a library developed for 10 years, and which is a fork of a previous library which was developed 20 years ago. So I work in a library already existing and already working, and which has been used to demonstrate some genericity capabilities in image processing. And we won't rewrite a new library from scratch after so many years of work. So that's why we are trying to find a way to make it more dynamic. I hope my answer was what answer your question.
Do we have more questions? Yeah. Can you come and talk to the microphone? Sorry about this.
So thank you for the interesting talk. So my question is, nowadays, neural networks are very fashionable in the domain of image processing. And in neural networks, we have the same problem that they're basically fixed for example, some input format and some color space and some size. So have you tried out, or would your methodology also work for neural networks or in?
So I said Pylen is an image processing library, which is true, but it's specialized in a specific domain of image processing, which is mathematical morphology, which can be used with some neural network. We did not use it with a neural network. Yes, we use it with neural network, but it's in a pipeline of applications. So neural network is in the Python part, and then we use the binary, and that's why we wanted to expose it to Python that have an end-to-end interface for this kind of application. Yeah, I hope I have answered your question.
Yeah, thank you.
I hope.
Okay, let's thank the speaker again. Thank you.
Thank you.